Welcome to physics class. My name is Moses Alagwa. I'll be taking you physics today. Welcome. Okay, welcome to class. Today we'll be doing a topic momentum for module 5. Linear momentum. Linear momentum has to do with momentum in a straight line, and momentum can be defined as the product of mass and velocity of a body. Product in the sense of mass times velocity, and it is measured in kilogram meter per second. That means for every object that is in motion, it has momentum, it has mass. So the product of its mass and its velocity is what we refer to as the momentum of that body. And then we'll go to impulse. Impulse can be defined as the product of the force and time of a force that acts on a surface. If a particular force acts on a surface, the magnitude of that force times the number of seconds that the force is in contact with the surface is what we refer to as impulse. For instance, if I give you a blow or a punch, the force with which I punch you times the number of seconds that my hand will be in contact with your face is what we refer to as impulse. So impulse is actually a blow on a surface, and is mathematically represented as the force of that blow times time, and its unit is Newton second. And then we go to Newton's laws of motion. There are 3 Newton's laws of motion. The first law of motion states that an object will continue in its state of rest or uniform motion unless acted upon by an unbalanced force. That means if I place an object on one spot and I leave it there, according to Newton, it is going to stay there forever, except a force acts on it to either change its position or cause it to start moving. And if I throw an object forward, it is going to continue going until a force makes it to stop. Then the second law states that the change in momentum of a body with time is proportional to the force applied on it. That means that the momentum of a body will change according to the force that is applied on it. If the force applied is big, the momentum change will be big. If the force is small, the momentum change will be small. For instance, if an object is moving and the object increases in velocity, let's say you are moving a car and you press the acceleration pedal, the car's velocity will increase according to the force that you apply to the pedal. So the force determines the change in momentum with time. If it's a large force, the change in momentum will be large. If it's small force, the change in momentum will be small. And you have the formula for Newton's second law on your screen, which is F is equal to change in momentum mass times velocity. That's final velocity minus initial velocity over the time of change, the final time and the initial time. We know that velocity over time is acceleration, so the formula can be reduced to force equal to mass times acceleration. And then we have Newton's third law of motion, which states that for every action there is an equal and opposite reaction. That means that according to the law of Newton, if I hit a wall or I punch a wall with a particular force, the wall will return that force back to me with the same magnitude in the opposite direction. We have the example up there of a rocket. As the exhaust is flowing backwards out of the rocket, it is pushing it forward. So the backward push of the exhaust or the fire is what is causing it to move forward. So this is the mathematical representation of Newton's third law, that for every action there is an equal and opposite reaction. The negative sign shows the opposite direction that the reaction force is to the original force. And then we'll talk of conservation of linear momentum. Conservation of linear momentum states that an isolated system, the total momentum of two or more bodies acting upon each other remains constant unless an external force is applied. In other words, momentum, we said, is the collision, is the mass times velocity of a body. So if two bodies collide, it therefore means that the total momentum of the two bodies before collision is equal to the total momentum of the two bodies after collision. In other words, if two balls, like we are seeing, hit each other, the momentum of the two balls, that's the yellow one and the blue one, will be equal to the momentum of the same two balls after they have collided. Yes, that's what the conservation of linear momentum is saying. And then here you have the formula, which finally gives that the initial momentum is equal to the final momentum. Momentum is not lost when two or more bodies collide. It is the same before collision and after collision. As conservation of momentum, the momentum is conserved. And then next we have a few examples that we are going to look at. It says two bodies, one moving at 10 meters per second, the other moving at 20 meters per second. When they collide, find the velocity of the 2 kg mass. That's the formula for conservation of momentum. m1u1 plus m2u2 is equal to m1 v1 plus m2 v2, where the formula before the equal is the initial momentum, and the one after the equal sign is the final momentum. Then you have it there. We also have that a body of mass 20 kg moves with a velocity of 5 meters per second. Calculate its momentum. Momentum is simply mass times velocity, so we have 20 times 5 equal to 100 kilogram meter per second. Then moving forward, we have another example. It says a mass of 4 kg moving with a speed of 20 meters per second collide with another mass of 5 kg moving at rest. Okay, it's at rest. Calculate their common velocity if they stick together after collision. It's still conservation of momentum. The only difference with this one now is that the two bodies, when they collided, they did not separate, they did not bounce off each other, they moved together. Okay, since they moved together, they have the same velocities. And then here's one more example. A force of 30 Newton is applied to change the velocity of a body of mass 15 kg from 4 meters per second to 6 meters per second. Calculate the time for which this force was applied. There we have, this is Newton's second law. The force changed the momentum, so we are calculating the time of change. Hence we make T subject to formula, and we have 1. Thank you very much for watching this class. I hope you understand. Please try out the questions in the leading questions and then your quiz.